My screen is visible.
Yes, ma'am, visible.
Okay. So in the last lecture, second half of the last lecture session, we saw this algorithm, right? Finding the convex hull of a set of n points in the plane. And this notion of convex hull is also defined for higher dimensions, right? In 2D, by the way, the algorithm that we had discussed, it's known as Jarvis-March algorithm. I forgot to mention it that day. There are other algorithms as well to find the convex hull of a set of points. There are many. In fact, like you take the sorting algorithms like insertion sorting, merge sorting, quick sorting. There are like merge hull, quick hull algorithms which are based on the ideas of the corresponding sorting algorithms. There is one more very interesting algorithm which is Graham's scan algorithm, and that algorithm has a running time of order n log n. So in case my uh, so the algorithm that we had discussed had a running time of order n times k, where k is the number of points that lie in the convex hull. And this k can be small, it can be large as well. So when k is small, let's say it's some constant, then Jarvis March is very fast. It's almost linear time algorithm. It's linear time algorithm. But if k is large, if it is say order n or order root n, then it becomes really slow. So there is another algorithm which is by Graham. It's known as the Graham's scan algorithm, and this algorithm has a running time of n log n. So the other algorithm. It's not an output sensitive algorithm. So that only depends on the input parameter n and has running time n log n, irrespective of how many points are there in the convex hull. What is the output size? Okay. So as long as k is less than k is order log n, this is good. But if k is more than that, then there are other faster algorithms to find the convex hull.
But
So,
there is one
yeah.
confusion that
Mm-hmm.
in problems like this,
Yes.
is it possible that the time complexity depends not only on the number of these input points, but also on the relative configuration? I mean, how the points are positioned in space. Will the geometry that depends on the geometry of the problem will also
Mm-hmm.
contribute, or
So how the points are, how means you mean by their coordinates or something?
I mean, uh,
Yeah,
no,
like, okay, one example could be, let's say the points are like this. Let's say I had 3 points which define the triangle, this any arbitrary triangle in the space, and all other points are within this triangle. So my point set is, so forget about the triangle, my point set is these red points, all these red points. That's the input set. And then I'm asked to find the convex hull for these set of points. Okay? So of course the convex hull is going to be this triangle, where there can be like millions of points in the plane. Right? So this n number of points, the total number of red points can be really large. Whereas if you look at the output size, the number of points which define the convex hull, that is only 3. 3 points define the convex hull. Is your question related to such a scenario, or?
Yes, if you consider the second diagram on the top of
Yeah.
this
Okay, this one,
paper, the second one, the,
this
the
one.
one after that. Yes, yes.
Okay.
So if we want to try, so if we want to calculate get the convex hull of this one,
Yes.
I
So
mean, in
in
this,
that, yes.
but in this case, it will be complicated because
Why?
this is not a convex, non-convex polygon. So
This is a non-convex polygon, right? So if
yes,
I mean, for instance, let's consider this example. If I look at this simple polygon, which is essentially going through every point in my input set, this is not a convex polygon. It's a simple polygon which is capturing all the points. But then I am required to find the convex hull. So wherever there are those gaps, concave gaps, I want to miss those gaps. Right? So here in this case, let's say all the points are lying in this gray region, the gray region. Okay, just zoom in. Let's say all the points are in this gray region, and I want to find the convex hull. Again, the convex hull is going to be a triangle. So my only job is to really identify these 3 points, which we can easily do via this algorithm that we had discussed. Okay, so
okay.
don't think of the shape which covers all the points. I mean, there can be many polygons which cover all the points. For instance, this gray cover region, right, which has all the points, is covered by the polygon that we have drawn. But what we are interested in is a convex polygon, right? The smallest possible convex polygon which cover all the points. So in fact, the Graham scan algorithm, the other algorithm um, that is used to compute the convex hull, it actually goes on finding these kind of concave regions and merging them or kind of ignoring them by using a data structure known as a stack. You must have already know what a stack is. So it uses a stack in a very clever way, and then wherever it sees this kind of a turn, it will just ignore this point and instead take the next point as this point. Okay, and the algorithm that we had discussed, it's a very simple sort of gift wrapping algorithm. You know, the way you will actually go on to wrap a gift, it's similar in that nature. So you find the one of the extreme points, like we took the leftmost point, and then we wanted to find the next leftmost point, and so on and so forth. So it's like actually wrapping a string around the set of points. So both follow a different, both this Jarvis Marsh and the Graham scan, they follow different strategies. If you're interested, go and, now that you have understood what a convex hull is, just go and search for this Graham scan algorithm. That is also simple algorithm. It uses a stack to compute the convex hull, and the running time is n log n. Okay. Any other question in for this convex hull related to convex hulls? And is convex polygon clear? Because we will see another problem based on convex polygon. That is also a very interesting problem. Yeah, please go ahead.
This problem is clear to me.
Sorry?
No, I said this problem is clear to me. Your explanation.
Clear, okay. And also the definition of convex polygon is clear.
Yes, ma'am.
Okay. So let's now look at the problems that I have planned for today's session. So the first one is, again, I'm going to discuss some geometry problems today, right? So hopefully we'll cover two problems on geometry. One, we will see how to apply sorting algorithm to find a polygon, not a convex polygon, but a simple polygon. And the other problem would be where we will be given a convex polygon, okay, and we want to find something called as the tangent points in the polygon. So the first problem is about sorting, the second is about searching. And it if you understand this linear search and binary search, then how do we really apply those simple algorithms in geometry problems? So that would be very interesting. The second problem, first problem is also interesting. Essentially it's like applying the merge sort algorithm but over a very different kind of problem, not on two linear arrays but um, on polygons. Okay, so let's see the first problem. So give me some time, I'll draw the figure first. Meanwhile, you can try to recap or recall what how merge sort works in linear arrays. So if you have an array of numbers or ordered, if you have an ordered list, meaning that the numbers can be compared, or the elements can be compared, how do we sort those elements using merge sort? So those, if does everyone know how merge sort work?
Yes, ma'am, it is covered.
It is
Videos.
covered. Others know how does the merge sort work?
Yes, ma'am. Like basic knowledge is there, but can you revise it once, like also?
Okay, we will do a quick revision. We'll do a quick recap before I come to this problem. So let me just plot the points and then I'll go through the merge sort quickly and see how to apply merge. And then you should be able to see how to apply merge sort to solve the geometry problem we are looking at. I have origin. Then it's 4 points. And we need some blue points as well. This. So for now, ignore the colors of these points. Let me first describe the problem that we want to solve. Then I'll cover merge sort on arrays and we'll come back to this problem next. So for now, ignore the colors of the points. I have these points, including the origin. Origin is fixed. The point 0, 0, that is fixed. And other than this origin, so let's say these points are stored in some array where at the 0th index, let's say the array begins at index 0. At index 0, I have the origin. And at the remaining indices, I have these points. Okay. And these points, it could be like this is point number 1, that is 2, 3, 4, 5, 6, 7. In any arbitrary order, all the remaining points, the n number of n minus 1 points, they are stored in indices from 1 to n or 1 to n minus 1, doesn't matter. Now, the goal is to find a polygon, a simple polygon, which goes through all these points, which, whose vertices are these points. So essentially what we want to find is, let me draw that figure. I want to find this polygon starting at the origin. Right? So this should be my first point, and that's the second point, the third point, fourth point, fifth point, sixth, seventh, and back to the origin. This is the figure I want. So figure in the sense, see, initially it might be the case that this is point 1, that is 2, 3, 4, 5, 6, 7. So these are stored in an array, where these points are indexed from 1 to 7. I want to sort these points in such a way so that this point becomes, comes to the index 1. Then this is the second point, third point, fourth point, fifth point, sixth point, and seventh point. So if I can sort these points so that, this is the indices we obtain, then essentially, I have actually this polygon, going from 0 to 1 to 2 to 3 to 4 to 5 to 6 to 7 to 8. Right, and this polygon is a simple polygon. Simple polygon in the sense that no edge will cross itself. It won't be like that. Okay, no two edges will cross. This is my first edge, then that's the second edge, the third edge, fourth edge, fifth edge, sixth edge, seventh, and eighth edge. So is the problem definition clear? Let me take a simpler example with fewer points. Let's say initially this was my point. The origin was at index 0. Okay. And then the remaining points, the remaining 4 points, let's say this is at index 1, this one is at 2, this is at 3, and that is at 4. Then, the kind of polygon I can visualize here is this. 0 to 1, okay, 1 to 2, 2 to 3, 3 to 4, and 4 back to 0. Can you see that this is also a polygon? The orange figure that I have drawn. See here, these points are stored in an array, a linear array. So here I have origin is stored, point with coordinates 0, 0. At 1, whatever are the coordinates of this point, that point is stored here. Then point 2, point 3, and point 4. This is the array I am given. I'm just drawing it in the 2D plane. And if I try to connect these points in this order, in the order of the indices where they are stored, then also I'm going to get a polygon 0 to 1, 1 to 2, 2 to 3, 3 to 4, and 4 to 0. So polygon is a region in the plane which is bounded by straight line segments. So this is a polygon. Okay. Why are you all quiet?
No, it is okay, but
Ah.
edges are crossing, so that's the difference.
Exactly, right? The edges are crossing, and therefore this is not a simple polygon. This is not a simple polygon. The question is, I want to find a simple polygon, or rather I want to sort these points in the increasing order of angles. So let me draw a line here. Consider this horizontal axis or line passing through the origin. What I want is, I want to sort these points in a particular order. So my first point in the sorted array must be, after 0, it must be the point number 3. And why? Because this angle is smallest. Point 3 makes the smallest angle with respect to the horizontal line I have drawn. Clear? Then the next point in my sorted array must be point 4. This one has a larger angle. Then it must be point 1. And finally, I must have point 2. So when I say that I want to sort these points with respect to these angles, what essentially I want is, and once I sort this array, I would want, okay, 0 remains in its own position, right? Then for first point must be 3, then it must be 4, next 1, and finally 2. That is the kind of sorting I'm looking for. So usually when you have simple numbers and you want to sort them, it's essentially, if I have two numbers A and B, I just compare whether A is less than B or equal to B or greater than B. Here I have points. If I have these 2 points, say 4 and 3, I want to know which one comes first. So here point 3 should come before point 4 because 3 makes a smaller angle with respect to this axis, with respect to this horizontal line passing through the origin. 4 makes a larger angle. So any 2 points you can compare with respect to the angles they subtend with the horizontal line passing through the origin. And once I have obtained this sorted order, 3, 4, 1, and 2, if I now try to get the polygon that I'm going to obtain, that is going to be a simple polygon. There won't be any crossing edges. So I start from 0, go to 3. Then the next point in my sorted order is 4, go to 4. Next is 1, I come to 1. Then it is 2, and we are done. So back to the origin. So see the difference between the blue polygon that I just drew, this blue polygon, and the orange polygon that I had started with. So this is going to be a simple polygon always. So you can even forget about the polygon thing. The problem is you are given these points in arbitrary order. They are stored in an array from indices 1 to n. At 0, we have the origin. And now the goal is to sort these points from 1 to n in such a way so that in the increasing order of these angles. Okay. And once you have sorted the points in the increasing order of these angles, if you try to draw a polygon, that polygon is going to be a simple polygon. No two edges are going to cross each other. Is the problem statement clear?
Ma'am, just because we chose the uh, angles sorting in increasing order, that is why this polygon is simple.
Yeah, yes.
Okay.
Initially also, it really depends how your, so for instance, the ordering that I took, 1, 2, 3, and 4, that actually gave us a non-simple polygon. But okay, is it possible that any other ordering can also give us a simple polygon? Let's say I had one. I mean, some other ordering can also give us a simple polygon. So for instance, let's say I had just these 3 points. Okay, and this is at point index 0, this is at index 1, this is at index 2, then definitely it's going to be a simple polygon because 1 subtends a smaller angle in comparison to the point number 2. Also, if we had this at index 0, this one at index 1, that as index 2, again we would have got a simple polygon. So it's not that just by sorting the points in the increasing order of angles. So I hope you understand what I mean by angle. Just by sorting the points in the increasing order of angle, that is not the only way to guarantee a simple polygon. There can be other ways as well. Our problem is that sort the points in the increasing order of angle so that it's guaranteed that the resulting polygon is a simple polygon. Okay, so the main goal is essentially to sort these points in the increasing order of angles. Okay. Is that clear?
So are we measuring the angles here or?
So we will not actually go, we are not going to actually measure the angle because those will involve computing those inverse trigonometric functions, right? So for instance, let's say for this point, I want to measure this angle. So you know that, right? Tan theta is perpendicular over base or some of those trigonometric function, and then theta would be tan inverse of P over B, right? This we want to completely avoid. What we really want to use is from day 1, I think, or day 2, I think in the previous session, we discussed about the CCW test. Right? CCW is, it will take 3 parameters, 3 points, P, Q, and R. Just a quick recap of CCW as well, because that is the simple test we are going to use to compare the angles formed by 2 points. So CCW, it will take 3 points, P, Q, and R in the plane, and it's going to return me a negative, a positive, or a 0 value, 0, or it can be greater than 0, less than 0, depending on how these points are oriented. So if there are just 2 points, we know that they are always going to be collinear. Right? Any 2 points, I can draw a line passing through them. But if there are 3 points, they also can be collinear. In that case, CCW is going to return me a value 0. So if P, Q, R are collinear, and the other 2 cases are whether this point R is to the left or to the right of PQ. So essentially, when you have 2 points P and Q, they are going to separate the entire plane into 2 halves. Okay, so I'm drawing this line, a directed line from P to Q. So it's, whatever it's the plane is, it's going to separate it into 2 halves. One is this side and the other is this side. So whether R lies in this half or this half, the value will be positive or negative. So if R is to the left of PQ, so left meaning this side, then it is to the left, and right is this half. As in, think of that you are actually moving along this line, and now you want to move towards the point R. So you were moving along this line. If I want to move towards a point in this region, I'll have to take a left turn. Right? If you want to move towards somewhere, a point in this region, I'll have to take a right turn. So you were moving in this direction. And then whether my point R lies to the left or right, the CCW test will return me a value either positive or negative. So this greater than 0, we usually use it for the case when R is to the left of PQ. I mean, we will use this convention. You can define it so that greater than 0 means right or whatever. And the third case is if it is to the right of PQ. So those are the only 3 possibilities. Given 3 points in the plane, their orientation can either be collinear, all the 3 points lying along the same line, then R will lie in this line, or R is in this region, so you were going in this direction and then you have to take a left turn, or R lies in the right half, going in this direction and then you have to take a right turn. Okay, so there is the CCW test which can be implemented just using the concept of slopes. You can find the slopes of lines PQ and PR and accordingly implement this CCW function. So in this problem, we are not really going to compute these angles. That is also one way of solving the problem I had stated, because I want to sort these points with respect to in the increasing order of these angles. So one way is that you actually go on and compute the angles and then sort the points by the angles. That is definitely one way. But that involves computing those complicated inverse trigonometric functions. So we want to avoid that completely. Okay. Instead, we will use this simple CCW test, which is only based on computing the slopes. We are even hiding the implementation of CCW. I just want to use CCW to sort these points. Okay. So is the setup clear now?
Yes, ma'am.
Okay. Now, the problem that we want to sort these points in the increasing order of angle, it is a sorting problem. I want to apply merge sort, let's say, to solve this problem. Okay. So now how does merge sort works? I'll quickly, just 2 or 3 minutes we'll spend on that. So let's say I have an array. Let's say I have an array of size 2 to the n, let's say 8. So the elements are A1, A2, A3, A4, A5, 6, A7, A8. And what it does is it partitions the array into 2 parts, 2 equal halves, almost equal halves. So I'm assuming that's an even sized array. In fact, it's a power of 2, so that every time, whenever we divide the array into 2 halves, both the halves carry same number of elements. So if it is not even, then you can do n plus 1 and n, right? So if it is 2n minus 1, then you can have 7 say points, and in one half you will have 3 points, in other half you will have 4 points. That really does not matter. So I'll have I divide this array into two parts. Okay? So the left half will have points from A1 to A4, and these are not ordered, right? So goal is to really order them. And the other half will have points from A5 to A8. And we keep on doing this division step. So again, this left half we are going to divide into two parts. First half will have points A1 and A2, second half A3 and A4. Same way. This is not the order in which the algorithm actually runs. And divide them here as well. Okay, so it's going to run in this order. I first take this entire array, split it into two halves, so I get these two halves. Consider this left half. Again, you split it into two halves, A1, A2, A3, A4. Then take this left half, split it into two halves. I'll have single-sized arrays. And at this point, the recursion stops. So here I have an array which has size 1. That means it is already sorted. So it's a divide and conquer technique, right? A recursive technique. And in recursion, you keep on dividing the problem into smaller sub-problems, smaller instances of the same problem, until you reach to a point where the problem can be solved in a trivial manner. Okay? So here I had its array of size 8, then I got it down to an array of size 4, then to 2. Finally, I get an array of size 1, which we know is already sorted. So we are done. I mean, the recursion stops. Similarly, A2, it's a single sized array, sorted. So once I have solution to two sub-problems, right? Because solution meaning sorted in this problem. Once I have two sorted arrays, the problem is to merge them so that I can obtain a solution to this problem. Okay, so let's say the values were, this was 7 and this was 8. So when I merge them, I'm going to get this array 7, 8. So during merging, we have to apply some, we have to really compare the elements and then put them back in this array so that the elements are sorted. Right? So I'll just compare 7 with 8, whichever is smaller, in this case 7. I'll place 7 at the first index and then 8 at the second index. Then go to the second, this part, and we'll repeat it for A3, A4 as well. So here again, the recursion stops, and then you merge them. So I'm going to show the merge step like that. You merge A3 and A4 so that A3 and A4 get sorted, right? So let's say here the elements were 1, 2, and 1. Then after sorting, I'll have A4 here and then A3, which is 2 and 1. Then in the next step, this part is sorted, this is sorted. Oops, this should have been 1 and 2. So these two arrays, sub-arrays are sorted. Now the goal is to merge them so that this array gets sorted. So when you want to merge them, you are going to compare the elements, right? So 7 you compare with 1. So 1 is smaller, first you'll have 1. Then you compare 7 with 2. 2 is smaller, so 2. And then since this sub-array is exhausted, I'm going to just copy the remaining elements from this left sub-array into the remaining position. So 7, 8. So that is how we get a, so earlier they were not sorted. right? So earlier we had 7, 8, then A3 was 7, 8, 2, and 1. Now they are sorted 1, 2, 7, and 8. And the same process we will follow for the second half, right? So once this is sorted, the algorithm will return to this second half, keep on dividing two halves, again divide, divide. And once you have these sorted arrays, merge them. This part will get sorted, then sort this part. Again, merge these two sorted parts so that this gets sorted. And once I have, these two sorted parts, I'll finally do this merge and this entire array will be sorted. So that is how the merge sort works. Okay. Any doubt in the merge sorting algorithm?
So it starts from down to up or up to down?
Sorry.
Does it start from A1, A2, like from bottom to up, or from topwards? Like how does it start?
Initially it was top to bottom, right? We started with this array. Then we split it into two arrays. Then this part gets split further. And so that's, until we reach the base step of the recursion, it's going from top to bottom. And once we hit the base steps, then it starts merging them in a bottom to top manner.
Okay, ma'am.
Okay. Yes. If you are seeing recursions for the first time, I would highly encourage you to, process these, especially this merge sort and quick sort. Once you have understood these clearly, at least this how this recursion works will be clear to you, and that should be because in the later uh, weeks of the course, when you see this, I think in the graph algorithms we do not really have a recursive algorithm. BFSD, even DFS is there. That's a recursive algorithm, right? So this recursion is very important to understand. So it's like it uses a stack inherently. So when I drew the figure, you were seeing all these parts there simultaneously, but that's not the case, right? Initially, I'll just have these two parts. Then I'll just have these two parts. Then I just have these two parts. Once I have these two and they are solved, I'm going to solve this subproblem. Then I'll come to this one. Again, split, solve these subproblems, merge them. This gets solved. Once these two are solved, these do not exist. The lower parts don't exist. Once these are solved, my goal is to conquer. I mean, in this sorting problem, I want to merge these sorted subproblems so that this one gets solved. And then I can completely forget about this part. Once this is solved, then I move on to the right part and repeat the same steps there. Once this is solved, forget about this entire part. My goal is to merge these two sorted arrays to solve this problem. Read books also. You can take Corman's or which book are you following for this course? You don't have to read the entire text, right? So, for instance, this Corman is really a thick book, but some chapters, let's say merge sort and quick sort are very, especially I really like the explanation of quick sort in that Introduction to Algorithms text by the CLRS textbook, 4 authors. Read them, read thoroughly. That will give you a better understanding of the algorithm, how to write the algorithms, how to prove the correctness of an algorithm, everything. That is very well explained there. Okay, so in this entire merge sort algorithm, the real thing happens during the merging step. That is earlier when we are going from top to bottom, we are just splitting the array at the middle half. That is all we are doing. But when it comes to merging the solved subarrays, there you have to apply some algorithm. You have to do it in a proper way so that you can solve the larger problem. So this how you implement the merge step, I mean, the essential work is done during the merge step. And that is opposite of what we do in the quicksort algorithm. In the quicksort, the essential work is done in the division step, how you actually divide the array. Merging is very trivial in the quicksort algorithm. Okay, you essentially find the pivot element, I mean, whatever, let's say, the first element or the last element, whichever element is the pivot element, you want to find the correct position of that element in the entire array. So there you are doing more work. Right? And once you have find the position of that element, you are not going to touch that element. The position of that element will then divide the array into two other halves, one which are smaller than the pivot, the other which are larger than the pivot, and you repeat those steps. So nothing really happens in the merging step there. Whereas in the merge sort, everything essentially happens in the merge step. Okay? The real work happens in the merge step. So we only need to understand, let's say somehow via this recursion, we have solved these two subproblems. Via recursion, we have solved. Now, how do we merge these two solutions to get the solution to this original problem? That is all we have to understand in the merge sort algorithm. Okay, so let's come back to the geometry problem. Now, all these points that I had, right? 7 points that I had from index 1 to 7, let me split them into two halves. Okay, so one is this blue half and the other is the red half. So it is possible that the indices were like this. Let's say this was my first point, then the second point, the third point, fourth point, and then I had fifth point, sixth point, and seventh point. So initially, let's say whatever the coordinates of these points are, they were stored in the array in these indices. Okay, so this point was at index 1, this is at index 2, 3, 4, 5, 6, and 7. So I have this array of size 7. I mean, at the 0th index, I have the origin. And then 1 to 7, I have these points. Right? So in the merge sort, what are we going to do? We are going to split those 7 points into two halves. So here I had split them like this, 1 to 4 in the first half and 5 to 7 in the second half. Okay. Does that red and blue make sense with respect to the merge sort algorithm? I'm just focusing on this first step. So this is my blue points and these are my red points. Okay. Okay.
Okay.
Yes.
So now look at these blue points. My goal is to sort these points in the increasing order of angle. So recursively, merge sort will take care of it. And after sorting, this should become the first point. So this should become the first point. How do I? Okay. So I'm going to use blue color to denote the indices after sorting. So this has the smallest angle, then this point, second point, third point, and fourth point. Right? So that if I consider the polygon which covers these points in this order, I'm going to get this polygon 1, 1 to 2, 2 to 3, 3 to 4, and back to 0. So I have already obtained this polygon. It's difficult to draw. Please excuse me for this. It's not getting at the, it's not starting at the point 4, but yeah, this is the polygon we'll get. Okay. And how did we get to sort these points? Just the way I explained here, right? So I had these 4 blue points. I'm going to split them further into 2 sets of 2 blue points, right? These 2 blue points, again, they will split into 2 singleton sets of blue points. And then when I have these 2 blue points, I want to sort them. When I'm going to merge them, I'm sorting them. So if I have 2 points, how do I compare them? Whether which one comes first and which comes second? So let's say some 2 points I had, 2 blue points, P and Q. And I want to know whether P should come first or Q should come first. What am I going to do?
Apply the CCW test.
CCW test. And what is the third point I'm going to take? For CCW, I need 3 points, right? CCW requires 3 parameters, P, Q, and R. So I have these 2 points, P and Q. What is the third point I should take?
The origin.
Origin, right? Good. So I'll take origin, P and Q. And then if so assume that no 3 points are collinear. Let's say the input is so that no 3 points are collinear. Then I just have to check whether the CCW returns me a negative or a positive value. Okay. So if I have just 2 points, it's going to be something like this. Say that's the origin. And then I have 2 points, P and Q. Let's say that's P and that is Q. Okay. Of course, this angle, the angle subtended by point P, which is θ1, and then angle subtended by point Q, let's say that is θ2. So I know that, I can see that θ1 is less than θ2. It means that P should come before Q. So, I mean, this notation does not make sense here. P less than Q, I cannot write like that, but essentially the point is, I mean, when I'm using this notation, I mean that in the sorted order, P must come before Q. That is all I mean. Okay. This comparison here, this less than here does not really make sense. I'm just using this notation to say that P must come before Q if θ1 is less than θ2. Okay. And based on this, if actually P were come to before Q, what should CCW test return to me? So if you look at the orientation of Q with respect to 0 and P, where does Q lie?
To the left of P.
To the left, right? And to the left meaning it should return me a value which is greater than 0. So all I need to do is, when you implement merge sort or you write a pseudocode for the merge sort, there you have those comparisons, right? So you have this left subarray. Let's say this is array A and this is the right subarray, or let's say this is array L and this is R. And you take some point in the array L at index I, Li, and some point j, some index j in the array R, so Rj, and you compare those 2 points, right? So if you have something like this, if Li is less than, let's say all the elements are distinct so that we don't care about the equal to equality. So if Li is less than Rj, then in A at index k, I'm going to put Li, else I'm going to place Rj in AK. That is how you implement, that is how you compare two elements and take the element which is smaller in the bigger array. Okay, so that was array A, this is L, this is R. You take some point here, compare them, and which one should come first? That depends on the comparison between Li and Rj. So when you want to sort the points with respect to their angles, then I'm going to replace this comparison because I cannot compare 2 points directly. I essentially want to compare the angle subtended by those 2 points, and that also we can completely avoid by just replacing this statement with the CCW test. So I will not have this, but I'll have some version of CCW, the point 0. The point is stored at Li. So let me denote those points by blue and red points. So this is Bi, some point Bi, and some red point Rj. And if CCW returns me a value that is greater than 0, if this is greater than 0, then in the original array A, I'm going to take the point. Which point we will take? So if it is greater than 0, this is equivalent to saying that theta 1 is less than theta 2, which is equivalent to saying that P is less than Q, right? So less than under quotes, meaning that P must come before Q. Okay. So in this, I'm going to take Bi, else AK must be Rj. So is this clear?
Ma'am, what is B
Yes,
here?
ma'am.
I couldn't.
What is B and R here?
Yes, ma'am.
Just these points. Okay. Let's say that I initially had this array A of all the points, where at index 0 I had this origin, and at the remaining indices I have these 7 points. Then in the next step I'm going to split it into 2 halves. So I'm calling this left half as the blue set of points and the right half as the red set of points. That is what I mean by B and R.
Okay, ma'am.
Okay. So similarly, we will sort the red set of points. Right? So initially the red points had indices. This one was at index 5, then 6, then 7. After sorting, this remains at 5. This becomes index 6. And this is at index 7. Okay. So that we get the simple polygon which covers these points 0 to 5, 5 to 6, and 6 to 7. Now once I have these two sub-arrays sorted, this red set of points and the blue set of points, then the final step is to merge these two arrays and get the sorted array A. That is our final step. We finally want to sort this. So now my array B will have these points in this order. First is 0.5, then this, then this. Sorry, B will have these points 1, 2, 3, and 4. And red will have these points 5, 6, and 7. Now I want to merge them. Okay, so look at the first point in the array B. It is this point. Look at the first point in the array R. It is this point. So I'm going to compare these 2 points. And which one should come first? Between these 2 points?
The red point, 5.
Red point, right? Point number 5. So in the array A, at the first index, I'll have 0.5. Then my current points are in the red array, it's this point, and in the blue array, it is still this point. So I'm going to compare these 2 points. And we can clearly see, I mean, we can see here because it's a geometry problem, we can visualize things, but you can, when implementing, I'll invoke the CCW test for these 2 points with respect to the origin, and we'll know that 1 must come before 6, right? So this blue point must come first. So the next index will be point number 3 from the original array. I mean, I think I have messed up these numbers, but I hope you understand it, right? So the next point in this sorted array would be this point. So in the next iteration, I'm going to compare this point with this point and keep on invoking the CCW test. So this point will come. Okay. So next step, this point and this point we compare. So the red point will be smaller in the sense that it has a smaller angle. Then next step, we are going to compare these 2 points. This point has a smaller angle, so this goes to A. And in the final step, I'm going to compare these 2 points where this point has the smaller angle, so this goes to A. And finally, I'll copy this point to A. So that is how we are going to get the entire sorted array, and we'll get the final polygon as I'm not going to draw the polygon. I'm going to get this final polygon 0 to 5, then to 1, then to 2, this point, like that. That will complete my polygon. So is it clear how this merge sorting works for this problem? Everything remains the same. You know, the entire skeleton of merge sort, we are following that same skeleton, except that here these numbers are not directly comparable. No, numbers in the sense, the elements in the sense that points are not directly comparable, right? We have to compare them based on the CCW test. So in the merge sort, wherever you had this comparison where you want to compare the elements, you have to implement the appropriate function. So in this problem, it was the CCW test, or you can compute the angles and compare the angles directly. So clear?
Yes, ma'am, it is clear.
Okay. Running time remains the same. It's because it's a divide and conquer based algorithm. The recurrence relation will be, you had an array of size n. You want to solve, let's say the time taken by merge sort is t of n. So the way it works, it divides the problem into 2 sub-arrays. So that is why this 2 here, and solve them. So t of n by 2. And then, so this is the division step, right? Yeah, so I divide the problem of size n into 2 subproblems of sizes n by 2. Solve them. So it will take t of n by 2 time for each problem. And once I have the solution to the 2 subproblems, I'm going to merge them. Merging takes order n times. So that's the recurrence relation which you can solve using the master method or the recursion tree method or the back substitution method or guess method. And this implies t of n is big O of and log in. Okay. So let's take a short break here, 10 minutes break, and then we will see the other geometry problem. And I also wanted to cover one simple problem and just ask you to solve it. So we'll cover those two problems in the next, yeah, it will take some 40 minutes or 30 minutes. So we'll take 10 minutes break here. So please do not leave the meeting. You can stay connected. We'll resume it at 4:20. Okay. Shall we move on to the next problem? If this is clear, especially the CCW test.
Yes, ma'am. That's clear.
Okay. Now, let's say we are given a convex polygon. So when we say we are given a convex polygon, meaning, so for instance, as in the beginning of the lecture we discussed, right? This is a convex polygon. So given this polygon as an input means I'm given the vertices of this polygon in either clockwise or counterclockwise order, in the cyclic order, right? Because if the ordering is not given, then it does not make sense, right? So let's say this is point 1, this is point 2, that is 3, then 4 and 5, and then it is not a convex polygon anymore. Right? So I'll go from 1 to 2, then 2 to 3, 3 to 4, 4 to 5, and 5 back to 1. And this figure is not a convex polygon. It's not even a simple polygon. Okay, so the ordering really matters. Okay, so either it is should be clockwise or counterclockwise, and since this is cyclic, it does not matter which is the first point. Okay, so any point could be the first point. So let's say this is first, and let's say the points are given in clockwise order. So 1, 2, 3, 4, 5, and then I know that the polygon that I will obtain by connecting these points is going to be a simple polygon, plus it is also going to be a convex polygon that is given to us actually. I mean, just the cyclic order does not guarantee convexity, but the input is such that it is a convex polygon. Okay. So our input given n vertex, so n is the input size, given an n vertex convex polygon. So essentially we are given the n vertices of the polygon. That is important. That is the n vertices. Let's say this polygon is P. So n vertices of P in cyclic order. To be more specific, let's say it's counterclockwise, it's clockwise ordering. Or it could be counterclockwise also. Let's assume it's clockwise. Okay. So we are given the n vertices of this polygon in clockwise order, such that when you connect those vertices, what you really get is a convex polygon. The goal is to find something called as a tangent point. Okay. The goal is to find, so I'll define what tangent point means, and there is something called as the left tangent point, the right tangent point. The procedure to find the left or the right is the same. Let's say I just want to find the left tangent point. This is what we are interested in. So what I mean by this is, before coming to the polygon, let's say all the points are, okay, let me define it with respect to the polygon directly. So I have a convex polygon, right? So let me draw a polygon. This is not convex. This is convex. Okay, so I have this polygon, and okay, it's not just the polygon, we also given a point and a point P, because the tangent point is defined with respect to a point which is outside P, outside the polygon P. Find the left tangent of point of polygon capital P with respect to the point small p. So this point can be anywhere outside this polygon. Let's say it's over here. Now, what I mean by a tangent point is like this. So assume instead of this, you know what a tangent means with respect to a circle, right? So if I had a circle to begin with, let's say I had a circle, okay, and I'm given a point outside this circle. I want to find the two tangents from this point to the circle. Those are going to be these lines, right? Those which just touches this circle. And the points where this, you know, right? The tangents from a point to a circle. They can be exactly two tangents from a point outside the circle to the circle.
Yes, ma'am.
Yeah. Now I'm calling this as a left tangent. I should call this as right one. Yeah, let me call this as left tangent. I don't know, do we use this notion left tangent and right tangent with respect to circles? I'm not sure. So by left, I mean that the entire circle is to the right of that tangent. Okay, so even if it is not a standard term, a standard terminology with respect to circles, I'm just using it in the sense that I'm calling it as a left tangent because the circle is to the right of it. And similarly, I'm going to call this tangent as the right tangent because this circle is to the left of it, left of this tangent line. And the points where this touches the circle, these two tangents, this point and this point, these are the left tangent point and the right tangent point. Okay, so this one is the left tangent point, this is the right tangent point. Okay. Now we extend this notion of tangent lines to polygons. Okay. I'm given this convex polygon. Again, it's just a visual way of seeing this polygon. When I say as an input, I'm given this, all I'm given is these vertices in cyclic order. Okay. So given, and these vertices are stored in an array. So let's say it's an n vertex polygon. So I have these n vertices stored in an array from 1 through n. And besides that array, I'm also given this point. Now the goal is to find the left tangent point, right? So if I try to draw, this tangent line from point P to this polygon capital P, that's my polygon. That's the left tangent line. And the point where it touches the polygon is the left tangent point. This point is the left tangent. So I want to find this point. I want to find this point. Let me call this point as Q. This is the point I'm interested in. So there are so many vertices of the polygon, right? N number of vertices. Of these N vertices, I want to find this point Q, which is the left tangent point given this point P outside the polygon. That is my problem. So is the problem statement clear?
Ma'am,
Yes, ma'am.
so
Yeah.
here, should we find a new point for like left tangent point, or like
New
should
meaning?
we?
So I have these points, right? 1, 2 up to N.
Yes, ma'am.
N number of points. Of these N points, one of the point is going to be the left tangent point, exactly 1 point. Similarly, exactly 1 point will be the right tangent point. So if I draw the other tangent line to this polygon,
But according to that circle diagram, I think Q is the only point which lies on the left tangent.
by the circle, okay, this one.
Yes, ma'am.
So
So
Q is the
according to that,
left tangent point, yes.
so is Q the answer, or else we have to
Yeah,
find
Q is
something
the
else?
answer. No, Q is the answer. What I'm saying is because there will be two tangent lines from P. Okay, so one is this left tangent, the other is this right tangent. Accordingly, we will have a left tangent point, which is this Q, and a right tangent point. Let me call that as R, right? This is the right tangent point. And if you can design an algorithm which can find Q, you can use that same algorithm, just tweak it a little bit, and you'll be able to find R as well.
Okay, ma'am.
Okay, so the goal is to find Q. Okay, you can use that similar algorithm to find R. Now, how do we find this point Q? What is, so forget about this point R for now. Okay, I have this point, I want to find this point Q. What I'm given is all these points 1, 2, 3 up to N. What is special about this point which will help me decide that this is the left tangent point? And the answer lies in the CCW test. Can you see how to use that test, and on what points should I use that test so that it is clear, it can return me the correct left tangent point? Just give it some thought, and just to make the presentation simpler and clearer. So since these points are stored in an array, there will be a starting index, a point which is the point which is stored at index 1. So that can be either in this side, the inner part of the polygon, or the outer part of the polygon. So inner and outer meaning with respect to P. Okay, so this is the part which faces P. I'm calling this as the inner part, and this is the outer part. Okay, so the starting index 1 can be anywhere, either in the inner part or the outer part. So let's say it is somewhere here, somewhere in the inner part. So that is the index 1. Then I have the second point, and so on and so forth. So Q is actually third point. Right? So this is third point, then fourth point, and so on and so forth. Finally, I'll hit back to this point, which is the nth point in my input array. Okay. So 1, then second point, third point, and in the clockwise order, when I return back, this is the last point in my array. Okay. If 1 were here, the point at index 1 were here, then 1, 2, 3, and so on and so forth up to n. So in this order, I'm given this polygon. Now, what is special about this point 3 with respect to the CCW test, which will, help us identify this, that 3 is indeed the left tangent point.
It lies to the most extreme
This is an
end of
extreme
the,
point. Yeah.
yeah.
So
And
extreme in the sense, if I take this,
so with respect to P, maybe it is like to the most leftmost point.
exactly, right? Q is the leftmost point. Every other point is to the right of it. But if I, uh, there is, okay, so this is one way of finding the left tangent point. Find the leftmost point in this entire set of points. Okay. And we had discussed finding the leftmost point in, I think, the Jarvis-Marsh algorithm as well, because there we start with the leftmost point with the minimum x coordinate and then keep on finding the next. Okay, but one confusion I have, yeah, I mean, there is one misunderstanding here. Leftmost in the sense, dear, with respect to this line PQ. Okay. Leftmost with respect to the line PQ. Right?
Yes, ma'am, like
I mean,
leftmost with respect to
yeah,
external point P.
yeah, external point P. Whereas in the Jarvis-Marsh algorithm, there was no external point P. So we were, starting with the point with the minimum x coordinate. And then with respect to that edge, starting from that edge, whenever we wanted to find the next leftmost point, it was with respect to this point, the current point, which is the leftmost point. We kept on finding the next leftmost point. So here it is with respect to P. So one way to find the leftmost point with respect to P is essentially, you go over all the points and then use the CCW test to find the leftmost point. That is one way. Okay. But let's say I just want you to, I also want you to make use of the fact that all these points are stored, are given to you in a cyclic order, plus they form a convex polygon. Can you identify the point Q quickly? Like, I mean, say I give you 2 points of in this set, say point number 1 and point number 3. And I want you to find in constant time which of the two is the left tangent point. I give you 2 points, let's say 1 and 3, and ask you that find the left tangent point of these 2 points. Which one is the left tangent point in constant time? How would you do that? So the approach that you are suggesting will take linear time. There is something special about 3, which is not there, if you see some special property about 3, which does not hold with respect to any other point in this convex polygon.
It is the topmost point.
It need not be the topmost point. So for instance, I could have my polygon like this. Right? Still, it would have been a convex polygon, but this need not be the topmost point. Okay. My polygon could have been like this also. Still, Q had to be the left tangent point and not this point, which has even higher y coordinate. So this Q and R are not the topmost and the bottommost point. They are extreme points in some other sense. Okay, I'll give you another hint. What can you say about the neighbor points of Q, neighbor meaning the one that comes before and after Q? Look at their orientation and take any other point, let's say this point 1, and look at the point which comes after this and before this. How do their orientations differ? And based on their orientation, you should be able to identify which one is the left tangent point.
And one point lies to the left of Q and the other to the right of Q.
So
That will be
that
the tangent.
no. So the thing is, both you only mentioned, right, that Q is the leftmost point with respect to the line PQ.
Yeah.
Right. So it cannot be the case that one is to the left, other is to the right, because this is the leftmost point. Right? The thing is, if I look at this point Q and consider this line PQ, look at the neighbors of Q, right? The one that comes before Q and the one that comes after Q. Their orientation, they both lie to the right of Q. Both these points lie to the right of Q. And this is not true for any other point in this polygon P. Take any other point, take this point 1. Look at its neighbors. Now consider this point, line P1. One point is in the left half, another is in the right half. Take any point, P2. This point is in the left half, this is in the right half. P4. This is in the left half, this is in the right half. Even you take this point R. Okay. Both these points, they are in the left half. So the only point that satisfies the following property, that its neighbors lie to the left, both of its neighbors lie in to the right of this line PQ, is only satisfied by the left tangent point and no other point. Isn't that true?
Yes, ma'am. Yeah.
Yes. So for the right tangent point, it will be that both of its neighbors lie in the left half. For the left tangent point, the crucial observation here is that both of its neighbors lie in the right half. You take any other point, one neighbor will be in the left half, the other neighbor will be in the right half. And that is how you can, if I give you 2 points and I know that one of the point is the left tangent point, you can easily identify which one is the left tangent point in constant time. All you have to do is do a CCW test on the 2 points. Okay, so for this point, I'll do a CCW test on the point at index Q minus 1 and the point at index Q plus 1. So CCW, P, Q, Q minus 1 and CCW, P, Q, Q plus 1. And if both of them return me, so since they are to the right, if both of them are negative, it means that Q is the left tangent point. Is this clear to all?
Yes, ma'am. Yeah.
Yes, ma'am.
Yes. So now, given this fact that we can identify, given this property of the left tangent point, can you give me a linear time algorithm to find Q, find the left tangent point? So it's a searching algorithm, right? I am given these endpoints in a particular order, in the cyclic order. They lie in the convex polygon. And I want to find this point, the left tangent point. I know what is the property of the left tangent point, and I can check for that property in constant time. Now, I want you to come up with an algorithm to find the left tangent point in linear time. So you essentially have to do a linear search over the entire set of points, right? You'll first go to point at index 1, see whether it satisfies the property, then come to point 2, and so on and so forth. So whenever, at any iteration, you come to a point where both of the neighbors have the CCW test return a negative value, you will stop and return that point as the left tangent point, correct? Yes?
Yes. Yeah.
So, and at every iteration, I'm going to spend constant time. The number of iterations is, in the worst case, it can be n. I might have to check all the n vertices starting from 1 to n, because the point n might be the left tangent point. And therefore, this way of linearly searching for the left tangent point is going to take order n time. Now we want to do it in a more clever way. We want to find the left tangent point in log n time. We want to do some sort of binary search here. So how do you do the binary search? So for binary search, one um, prerequisite is that your array must be sorted. Then only you can apply binary search, right? So here also, the elements are sorted. Sorted in the sense they are given to you in this ordering. There is an ordering. 1, then 0.2, 0.3, 0.4. They have an ordering. So can I use this ordering and then find the left tangent point in log n time? The ideas remain the same. Whatever is the main skeleton of a binary search, where you have the the entire array. Let's say the indices from A to B. You go to the middle index. Let's say index C. Then see whether check whether C is the point you are looking for. If it is, we are done. If not, then we compare our query point with C. If the query point is to the left of C, we completely ignore the right half and just search in the left half. If the query point is larger than C, we ignore the left half and search in the right half, and then repeat this process. So every iteration, we get rid of one half of the input space, and therefore we can find, we can search for the element in log n time, because in every iteration, the search space reduces by a factor of 2. So now we want to do the similar thing here, right? So I have these uh, points stored in the array from index 1 to n. So let's say the starting index 1 is A, last index n is B. So that my initial search space is this entire set of points. Okay. Now I want to get rid of half of the points. So I will find the middle index. Middle index, let's n by 2, right? The index n by 2. So it can be somewhere here or here. And then I must use again CCW test to actually get rid of one half of the set of points. So either from A to C or B to C. I'll just get rid of those because I know for sure that there my left tangent point, my left tangent point cannot be there. So we just ignore that half and then search in the remaining half. How do we do that? So I'm just going to write the main key property of the left tangent point here. So CCW of P, Q, and Q minus 1, and CCW of P, Q, and Q plus 1. So both are going to be at the right. So this is less than 0, and this is less than 0. That is the identifying property for left tangent point. Yeah, so now using this, we can find Q in linear time. But now the goal is, can we do it in order log n time? Using binary search. For simplicity, I'm going to, so I'll explain this binary search ideas to you. I mean, I'll ask you also some questions, but it's very easy. Once you get the idea, it's easy, but it's very nice way of using binary search for a geometry problem. So let's say instead of drawing this convex polygon, I'll just draw a circle. Okay. For any convex polygon, I can draw a circumscribing circle. So just to keep the diagram simple, let's say all my points are lying on this circle. And there is this external point P. That's the tangent line I'm looking for. Or I'm actually interested in finding this point Q. Okay. So I have some convex polygon here. Okay. I'm just replacing it with a circle. And all the points are lying on this circle. So there will be some first point at index 1. So that I'm denoting by A. And the last point, which will just be before 1, that I'm going to denote by B. Okay. So somewhere I'll have A, the first index, and just the previous point would be the last index. Okay, point B. So since these points are ordered in the cyclic order we have, if I want to apply binary search, I'm just going to look at the middle index. Okay, so this is index 1, this is index n. Go and look at the point at index n by 2. That is what we do in the binary search, right? The first step of binary search. So let me call that middle index as C. So first thing to observe is the middle index can lie either in the internal part or in the external part, right? The middle index can be either on this side or that side. Okay. Yes or no?
Yeah, yes, ma'am.
Yes. Now,
Yeah.
if it is outside, then fine. If it is inside, then again, there can be two cases. So let me quickly copy this figure. Now things will be easy if you understand that. So let me call the middle index as C. C will be either on the right half, somewhere on the right half, doesn't matter where it is. Let's say it is here, or it could be in the inner half, inner part. Now, when it is in the inner side, then it can be either above A, okay, somewhere in this region between, this point I want to find, I don't know where it is, but it will be either in this region or it will be in this region, C. Okay, so there are two cases here. C can be either here or it can be somewhere here. So far, if there is any confusion, then let me know.
Ma'am, what is C? Okay,
C is
got it.
the
Yes.
middle index, middle index, right? So initially, A will have value 1, B will have value n. The middle index is, let's say, n plus 1 by 2 or something. I'm just calling it n by 2, the middle index. That is the point C, point at index n by 2.
Ma'am, I didn't understand why are we shifting it to left or right? I mean,
Which one?
the point C, like why are we shifting it to the left
No,
of
no,
A or
it is
right of?
possible. It is possible that C, the middle index, lie in this half or it lies in this half.
Oh, ma'am, but because if it
Between.
lies in the inner
Mhm.
half, then it cannot be the midpoint of A and B.
No, so why? Because it's the, the visually we are seeing this like that, and that is what is confusing us. It is possible that I have n by 2 points in this region and n by 2 points in this region, right? Here also, although it looks like, visually it looks, oh, C is so close to A, but isn't it possible that I have n by 2 points here? The points are very close in this region, and I have n by 2 points in this bigger region. We can,
Yes, ma'am. Like,
yeah, we can arrange the points like that. So close here so that, half of the points are in this small region and half are in this big region. And similarly, C can be below A. It cannot be between A and B because they are sitting next to each other. So if it is here, then what I mean is half of the points are between B and C, and half of the points are between A and C.
ma'am, then it
Okay.
is possible if there are a
Hmm.
totally less number of points. Like if there are only 4 or 5 points, then it is possible. But if there are many points, then it is difficult.
Why?
Like because the area is less. I mean, the length is less between A and C
It really does not
and B.
depend, right? How it's somewhere, some regions are very dense, some regions are less dense.
Okay, ma'am.
Yeah, you will have a big, if I have very, large number of points, it be a large polygon. Some points, some region will be dense, some not so dense, again dense, not so dense, and like that. Yeah, it's completely possible that I have just one point in the outer region and all the other n minus 1 points in the inner region. Completely possible.
Okay, ma'am.
Yes. Okay. So first thing that we need to identify is how do we know whether C lies in the outer region or in the inner region? Can someone quickly see this? Again, use CCW
with
test.
if
Uh, please
ma'am
go
is
ahead.
the left tangent, yeah, left tangent is known to us, or no, we are
No, no, no,
finding it.
no.
So
That we have to find,
yeah,
right? Yeah. So
right.
I know A, I know B, I know the point C because they are the input set of points. A is the index 1 point, B is the index n point, C is middle index point. So can I use, if I want to know whether C lies in this region, like this, or in the outer region, uh, I can I use CCW to identify that? It's again very simple. Just look at the neighbor of C. This is C. Look at C plus 1 and look at their orientation. P, C, and C plus 1. So you will be able to see that if C is in the outer region, then CCW test will return you a positive or a negative value. Whereas if C is in the inner region, then P, C, C plus 1 will return you a value of different sign. Because the
Ma'am,
points are in
but
clockwise
if
ordering. Huh.
yeah, but if C is below A and B, like in the inner half, then is
Huh.
this still applicable?
Yeah, so first thing is to identify whether C is in the outer half or in the inner half. For that, I'm saying that simply use the test CCW, P, C, and C plus 1. So if C
Okay,
lies
yeah,
in the outer
yeah,
half, it will give you a different value, different sign. And if it is in the inner half, that will definitely give you a different sign. Okay,
yes,
so
ma'am, this
that
is
way you
clear.
can
Yeah.
differentiate between these two cases. Now, when C lies in the inner half, then we have to do one more test to know whether C lies above A or below A. And that is again easy, right? I will use the CCW test for P, A, and C. So when C lies above,
Yes.
yeah, and here also C lies below,
Mhm.
so CCW will be able to identify. So I need to use this test, then CCW. In case C lies in the inner half, then I will use PAC and CCW. Yeah, just CCW PAC will help us know whether C is above A or below A. Below A, it means it is also below B. Once we have identified these cases, the key challenge is to check which part of the, which n by 2 point should I get rid of. So once I have identified C, first I will check whether C is the point I'm looking for. So if it satisfies this condition, then we are done. If not, then we have to search in one of the two halves. So here one half is A to C, other half is B to C. So where should I search for if we are in this case?
In the A to C region.
Exactly, right? Because I know that the points are in clockwise order. I know that C is in the outer half. I know that C is not the left tangent point. That left tangent point must be in this region. Okay, so we are going to just search in this region. So we'll get rid of half of the points and repeat. Similarly, if C is in the inner half, then we have these two cases. So where do we search for in if C is above A? So again, note that although there are n by 2 points here and n by 2 points here.
We will again search from A to C only.
No, A to C, it cannot contain Q. So C is in the
Eh,
inner side. A to C cannot contain the point Q. It must be
Okay,
between
yes,
C
in
and
the
B.
B to C region only.
Yeah. So it's like visually it does not it feels like, oh, this is the bigger region, but the number of points, as I said, right, it is exactly n by 2. So we will ignore this region A to C. N by 2 points we have removed from our search space, and we will simply search in this region B to C, C to B rather. Okay, is it clear to all?
Yes, ma'am. Ma'am, but is this binary sort or like how is it binary search? Like,
So
sorry.
binary search, the main idea is in every iteration you want to get rid of one half of the points. That is what we are
Yes.
doing here. So in every iteration, so suppose I was in this case, I got rid of these n by 2 points. So in the next iteration, my search space reduces by half. Okay. So once I have this as my search space, I'm going to rename C as B. So this is my search space, A to B. Again, I'll find the midpoint. Either it will lie outside in the outer region or it will lie in the inner region. Same thing keeps on repeating in every iteration.
And ma'am, the sorted array in case of binary search, this is equivalent to, we know that the order is like clockwise order of points.
Yeah,
Is
yeah.
it that?
This is
Okay.
clockwise and the points lie on, it's basically cyclic order. That cyclic
Okay.
order is helping us. Yeah.
Okay.
Right. And finally, this case, we will actually remove these n by 2 points. We will search from A to C. This would be our search space. Okay, so once that becomes a search space, I'll rename C as B. So this is point A, this is point B. Ignore all the points in between and repeat the process. Okay, so maybe you can try to implement all these or write complete pseudocode for this problem. So if there are any doubts regarding these two problems, we can discuss that in the next session. From next session, we'll leave these geometry problems and start working on this graph problems, right? So some algorithms, I'll just cover whatever is there in the lectures. I mean, again, a quick recap, not all the algorithms, but those which are important for us. And then we'll see more problems and some problems related to the topics covered in the course and some algorithms which are not covered in the course, that also we'll see. Okay, so we'll stop here. If there are any quick questions, we can take now or we can take in the next session as well. Okay, so should I stop the recording?
No. Yeah.
Okay. So thank you all
Yes,
for
I'm all
attending.
clear.
Sorry?
Yeah, all clear from me.
Okay, okay, dear. So we'll meet next Saturday and thank you all for attending.